Hello, I'm Monty.
And I am Eric. For task 1, we used a Python object to simulate a particle, storing x velocity and y velocity and incrementing time in small intervals and storing points in the list before finally calculating scales for our graph and plotting our point.
For task 2, we used a similar method of representing our points using Python, but this time we used incrementing x values and the projectile motion formula to find our y values exactly.
For task 3, we took in a coordinate to reach and used the formulae we derived to calculate the minimum speed. We then took a slightly above and below angle and plotted points for all three using the projectile motion formula as with task 2.
For task 4, we calculated the maximum horizontal range using the formulas derived on the slides, along with the angles which achieve this. We then used the projectile motion formula to find the points and plot the lines for the optimum angle, along with the angles slightly above and below this.
For task 5, we used the formula derived on the slides to calculate the points for the bounding parabola, drawn in purple, then plotted it along with the minimum u, high ball, and low ball, and the maximum horizontal range.
For task 6, we have taken in U and H and determined the distance travelled to both the theta, which gives maximum horizontal range, and theta equals 60. The graphs of both of which can be seen on the right, with the number present below.
For task 7, we iterated through x values, starting from 0, working up to the maximum horizontal range, and for each value, calculated the distance from the origin, and stored that along with the time it occurred at. We then plotted a graph of distance from the origin against time, which can be seen on the right.
For task 8, we gave the particle an initial u and theta, which are used to calculate its respective vertical and horizontal velocities. It then iterates through time with when it hit the ground, the vertical component of its velocity was multiplied by the coefficient of restitution and then flipped. I then used this to calculate and store all of the points it would travel through before having the specified number of bounces, and then used these points to calculate maximum x and y distances.
For task 9, we used object-oriented programming to have two particles, one which ran without air resistance and one which had air resistance. Both travelled under gravity for the same amount of time, leading to one affected by air resistance not hitting the ground.